Humans are prolific builders. We have radically transformed our environments with structures of our own design. Huge skyscrapers are particularly salient, but we are in fact surrounded by all kinds of ingenious physical structures that were designed and created by humans, like this carefully balanced rock tower and extremely funky cake. What cognitive mechanisms support our ability to reason about how structures like these were made? One strong candidate is physical reasoning, an understanding of how physical objects behave. There's been a lot of progress in our understanding of how humans make intuitive judgments about physical scenes, such as whether towers like these will fall. But we know much less about how people reason about how to build one from scratch. A second important mechanism is planning, the ability to think multiple steps ahead. We've made great strides in characterizing human sequential decision-making, but the vast majority of tasks used to study planning have been pretty abstract or have relatively low state-space complexity. There is less work on longer horizon planning that occurs in concrete, familiar settings. The goal of our paper was to investigate construction behavior in a domain that required both physical reasoning and planning. Our approach is inspired by work in developmental psychology, investigating how children reason about physical construction, and in particular developmental change in the pattern of errors made by children in Lego assembly tasks. We aim to complement these efforts by developing a standardized virtual platform for studying construction behavior in both kids and adults. Our paper also connects to recent efforts to apply deep reinforcement learning to develop artificial agents that can build 2D block towers according to a variety of different goals. We think that gaining a thorough understanding of how humans solve similar tasks will provide a path towards developing AI that behaves more like people in these settings. In this talk, I'm going to describe a new web-based environment for physical construction that enables precise and scalable collection of human data. I'll then present an experiment in which we test physical construction ability over repeated building attempts. Here we aim to answer 3 questions. How does practice affect construction performance? How does practice affect the construction process? And how are different people's construction processes related to each other? First, the building environment. Our interactive web interface allows people to build 2-dimensional block towers under simulated physics. In our study, participants were presented with an unlimited inventory of 5 different types of blocks, and we snapped these blocks to a grid to reduce motor noise. However, blocks can still fall if placed in unstable locations. We set out to assess how people approach novel construction tasks and to see how practice affects their ability to build. We therefore needed a task that was not trivially easy for people, that had a clearly defined goal with graded measures of success, and also allowed for multiple valid solutions. In our silhouette task, people aimed to recreate ambiguous silhouettes of target block towers. Participants saw a silhouette on the left and had to recreate it on the right using any configuration of the blocks provided. Participants had 60 seconds to recreate the structure, were incentivized for accuracy and speed, and we ended the trial early if a block fell. We sampled a variety of physically stable structures from our library of blocks and selected a subset of 8 silhouettes that would be difficult without planning and that could be reconstructed in a large number of distinct ways. Our main goal was to see the effect of building the same structure multiple times, but we also wanted to detect any task general learning, that is, improvement that isn't tied to a specific structure. So for each participant, silhouettes were randomly assigned to one of 2 groups, which I'll call control and repeated. Towers in both conditions were built at the beginning and end of the experiment, interleaved among the other structures. The repeated structures were built an additional 2 times, in between these first and final attempts. And in each of these phases, the order of the structures was randomized. This meant silhouettes were attempted twice in the control condition and 4 times in the repeated condition. So how does practice affect construction performance? Here's a heat map showing the distribution of where people place blocks on their first and final attempts. We can see that by their final attempts, participants placed fewer blocks outside of the silhouette and completed more of the structure. That with practice, people made fewer spatial errors. But to get a better characterization of how accurately people were building, we needed a measure that both rewarded people for recreating more of the silhouette, but also punished people for placing blocks outside of the target region. We therefore used the F1 score, which combines recall, the proportion of the silhouette that was reconstructed, and precision, which is the proportion of the reconstruction that fell inside the silhouette. The F1 score takes the harmonic mean of these two things and ranges from 0, with a totally empty reconstruction, to 1 for a perfect reconstruction. And here are some example values on the bottom of the slide. We found that participants' reconstruction accuracy was reasonably high on their first attempt, but far from ceiling, and continued to improve across attempts. But we also found that by the end of the experiment, towers in the control condition, those built for the second time, weren't significantly worse than those built four times, suggesting some amount of task-level generalization. We also found an overall decrease in how long it took people to finish building each tower. However, we only rewarded people for speed when they had perfectly reconstructed the tower, and so we thought we might observe a larger decrease in build time when they were doing well. We do find this. Perfect reconstructions are completed much faster across attempts. So we've seen that people learn to build more accurately and quickly. But how does the way people build, how does the way they're reconstructing these towers change across repeated attempts? To answer this question, we need to compare the sequences of actions used to build a structure across different attempts. Actions here are just block placements, where each block placement has a shape and a location. Intuitively, actions are similar if the blocks being placed are of a similar size and placed close together, and different if they're very different sized blocks placed further apart. We combine shape and location information in a vector containing the width and height of the block and its XY location, and computed the distance between two actions as the Euclidean distance between the two vectors. To compare whole sequences of actions across attempts, we took the mean of these distances. This gives us an action for action distance, which is a straightforward comparison, but strict with respect to the order in which people reconstruct the tower. For example, these two actions are identical, but don't contribute to this measure of similarity because they're performed at different times. To allow for the fact that people could make the same action in a different order, we also defined a best match distance, which remaps actions in the sequences to minimize the distance between them. We then used these measures of action similarity to ask how much people updated the way they build each tower throughout the experiment. We're going to look at the average distance between consecutive building attempts. A downward trend on this graph would indicate that people made larger changes between early attempts than they did between later attempts. We found evidence for such a downward trend for both our strict action for action measure and our best match measure that ignored the specific order in which blocks were placed. This suggests that individual participants tended to settle on a particular way of building each tower across repeated attempts. But what might explain this? We hypothesized that the more accurately someone builds a tower, the more likely they are to reuse actions from that attempt. Consistent with this possibility, we found that how accurately someone had built a tower on their previous attempt strongly predicted how much they updated their procedure, such that participants changed their procedure more dramatically when their prior attempt was less successful, but stuck with the procedure if they'd previously earned a high score. Practice then does affect the way people build. People make smaller changes to their procedures and do so in proportion to how well they did last time. Which raises our next question. Insofar as individuals are setting on a procedure for reconstructing these towers over time, how much consistency is there between the procedures that were discovered by different people? To answer this question, it's not enough to look at actions, even with this kind of temporal reordering, because people might make the same tower but out of completely different blocks. For example, here are two separate building trajectories that involve the same sub-solution but made from different blocks. We can visualize the commonalities in build trajectories with state space graphs like this, but adding a whole new trajectory to something like this doesn't really do anything unless it adds a new state or transition. We can make the graph more informative by using larger nodes to represent states visited by more people and thicker edges to represent state-to-state transitions that were made more frequently. Now, to better understand the structure of these problems, in other words, the constraints on the trajectories that arise just from the setup of the task, we constructed a baseline graph by running a simulated random policy agent. This agent places random blocks in random locations, but always in stable locations and always within the target silhouette. So to read this graph, it's the same idea that we get closer to the goal as we move up, So F1 score is increasing along the y-axis from the empty world state to perfect reconstructions at the top. And the horizontal position sort of roughly correlates to the center of mass of the reconstruction. And we can see here that the agent solutions are highly varied, and most stop short of the goal. Now compare this to the graph of the trajectories that participants took in their first attempts on the silhouette. Here the red lines indicate that part of the reconstruction falls outside of the silhouette. These are the spatial errors that we saw in the heat maps earlier. But if we focus just on the darker lines, you'll notice that there's quite a bit of variability in the solutions that participants discover. And in many cases, participants do discover a unique solution. On the other hand, you may also notice how much thicker many of the edges are in the human graph compared to the random agents. This reflects a fair amount of consistency between participants in the states they visited on the way to a solution. Together, these visualizations give an impression of both the variability and consistency between participants, even on their first attempts. On their final attempts, if anything, we see an increase in the consistency between participants. People seem to converge on a smaller number of trajectories through the state space. Now, to rigorously evaluate this possibility over all towers, we derived a measure of consistency which could be applied to sequences of states of varying lengths. The intuition behind this measure is that the more people that traveled through the exact same sequence of consecutive states, the higher the consistency. The specific measure we used is known as the Gini index, which we can apply to all subsequences of any length. For example, here are the subsequences of length 1, and here are some examples of length 2. So in essence, this is an n-gram analysis. Taking a look at our random agent baseline, we see a decrease in the Gini index as we consider longer sequences, which is what we would expect, because the more consecutive states kind of in a row that you consider, the less likely it is that that sequence is repeated exactly. Now compare this to what people did the first time they attempted these towers. We see that there was kind of reliably much greater consistency between trajectories for all lengths. Moreover, on their final attempt, sequences were even more consistent, affirming the impression we had earlier that participants seem to converge on more similar solutions over time. It's perhaps worth emphasizing now that this wasn't guaranteed by participants' greater accuracy across the experiment, because the full set of solutions found by participants across all attempts represents just a tiny fraction of all the possible ways of building each tower. Taken together, these results suggest considerable systematicity in human behavior on this task, specifically that people may share similar biases towards certain sub-solutions when reasoning about these problems for the first time, as well as similar methods by which they update their strategies over a handful of attempts. So to recap, we saw that repeatedly building physical structures makes people faster and more accurate at doing so. We showed that as people practice, they update their building procedures less, and in particular, the size of these updates is sensitive to how well they built the tower the previous time. Finally, we saw that people come into this task biased towards certain sub-solutions, and that their strategies converged with practice. In future work, we plan on using data from these kinds of experiments to constrain theories of how people hierarchically decompose complex problems into simpler subtasks. We also hope to provide a suite of tasks and metrics that can be used to guide the development of algorithms towards more human-like construction behavior, as well as contribute a shared tool for investigating developmental change in the underlying planning and physical reasoning mechanisms that support complex, open-ended behaviors. I'd like to thank my co-authors, Judith E and David Kirsch, as well as the members of the Cognitive Tools Lab at UCSD and the organizers of CogSci 2020. Thank you.